Oh, I see. That's how it works. All right. So then, welcome back, everybody. Well, thanks for listening to me, and thanks to Ambush for his amazing deep dive into regret minimization in stationary MDPs, and for describing the user analysis in such detail. So my approach is going to be like slightly different from what Ambush did. What I'm going to do now is going to be more of like a broad exploration of everything that is related to adversarial MDPs, which are MDPs where the reward function or the transition function is allowed to change over time. So what I'm going to try to do here is like try to understand first, like, what is this notion of an adversarial MDP? What is achievable in this problem? What is not achievable in this problem? And then try to give some algorithmic ideas and show you some basic algorithm design principles that will hopefully be useful for all of you for designing your own algorithms and coming up with better guarantees and better and more practical algorithms, or at least that is the main idea. So I have a lot of material. So yeah, please ask questions if you have some serious questions. But I'm gonna rely on Chava and Ambush to answer all the minor questions that come up on the fly. All right. So with that, let's get into it. Okay. So you've seen this picture a million times already. This is a picture of a Markov decision process, which is just an interaction between a learner and an environment. The learner takes an action. This is passed on to the environment or the transition dynamics. And this, together with the current state, is going to influence the future states of the environment. Okay. And what makes this problem interesting and why we love this problem is the presence of this reward function that allows us to specify all sorts of like beautiful tasks and specify a reinforcement learning problem. So this is a standard Markov decision process where all these elements are fixed. The transition dynamics that is labeled as the environment here, and the reward function is fixed. And these steps are repeated in a number of rounds indexed by T in this talk. All right, so this is the classic setup. What we're going to be studying in this talk is an adversarial variation of this problem, in which in each round T, there is going to be an external force, an adversary, that is going to have the power to change the reward function. That is going to be no longer a fixed function of lowercase r that acts on x and a, but rather is going to depend on time, can change between time steps. And this adversary is also going to have the power to change the reward function. So in each round, the next state is not necessarily going to be drawn from this fixed distribution P given x and a, but rather is going to depend on the action of this external force as well. It is going to change between rounds. So this is the idea. This is the setup that we're going to be studying. And what we're going to try to understand is like, what sort of assumptions can we make about the adversary that will enable efficient learning? What is learnable in this setup? What is achievable? What is not achievable, right? So we're going to try to cover all of these in this 1 hour, which is a very short time for this. All right, so we're going to be evaluating these algorithms in terms of their regret. Regret is, again, as has been defined a few times already during this workshop, it's just the gap between the cumulative reward of the learner. All right, so this is here on the right-hand side. This is the cumulative reward of the learner itself. And we're going to compare this cumulative reward to the cumulative reward of a comparator policy, right? So here, this comparator policy pi is going to be something that we try to compete with, right? So we are trying to do nearly as good as this comparator policy. And what's important in this regret definition is that these states, these xt star, x1 star, x2 star, this is the sequence of states that this comparator policy would have encountered had it been playing instead of the learner from day one, right? So this x1 star, x1, x2 star, and so on, these are the sequence. This is the sequence of states that the environment would have generated in response to playing actions from the comparator policy pi. So what you see here, really on the left, as the left term, this is really the cumulative reward that this comparator policy would have achieved had we run it from day one, okay? On these sequence of reward functions RT that we have encountered during learning. Okay, so this is somewhat related to this concept of a policy regret that Csaba mentioned after the talk of Alan and Walter. We can discuss more about the implications of this, but I want you to internalize this regret definition for now and understand that the sequence of states is different for both of these terms, right? So this is like really, in a way, the fair way to measure difference between cumulative rewards in this setup, right? And as before, as in the online learning tutorials, and also as in Ambuj's tutorial, our goal is to, well, come up with algorithms that have sublinear regret, which means that these algorithms are actually learning to perform in a reasonable way, or we are trying to understand limitations in terms of this regret. All right, so this is going to be our main performance measure. Okay, and with this in mind, this is the outline. I'm going to first present some hardness results. I'm going to show you some settings in which learning is known to be either completely impossible or computationally hard. These are going to be learning against non-oblivious adversaries and arbitrarily changing dynamics. And then I'm going to focus on the tractable scenario of just adversarially changing reward functions. I'm going to describe some key algorithmic ideas in that part. All right, so let's start with just hardness results. All right, so so there are different types of adversaries that one can consider in online learning, as has been described in yesterday's online learning tutorial as well. So the most powerful of these adversaries is the so-called non-oblivious adversary, sometimes also called an adaptive adversary. So this adversary, when selecting the reward and transition functions in this online MDP problem, when selecting RT and PT, it can take the entire history of interaction into account, right? So it can look at what your state right now is, what your past actions were, and what your past states were. And then based on this entire history, based on this knowledge, it is going to pick the reward and transition functions. Okay, so so this is a very powerful adversary, and turns out that in this online MDP problem, it is entirely impossible to get sublinear regret against such a non-oblivious adversary that can pick reward and transition functions according to the past history. All right, so the construction is very simple. Let me just move this little Csaba out of the way. All right, so so the construction is very simple for showing this property. Just consider this MDP, right? Just with 3 states, 2 actions. The 2 actions that you can take in the middle, right? So one of the actions is going to take you left, and one of the actions is going to take you right with high probability, right? So, for example, if you take the left action, you're going to move to the left state with probability 1 minus p, and then you're going to move back to the middle state, and then this procedure is going to repeat on and on. All right, so let's consider a reward function that is going to be chosen by an adaptive adversary in the following way. You're going to get 0 reward no matter what you do. So there's a default reward for every state that is 0, which is changed depending on the actions that you took in the past, right? So this is why you can already feel that this adversary is going to be very tricky to play against. So in particular, what this adversary is going to do is that it is going to give a reward of 1 to the left state if in the previous round you took the action that took you right, right? So you would only have a chance of getting a reward of 1 if you took a different action in the previous round. All right, and similarly, the right state gets a reward if in the previous round you took the action that takes you left. So again, you have no chance of getting this unit reward of 1 in this setup, right? So here you can see that this reward function takes the entire history into account in a way that completely messes you up. So you can see that you're going to be getting 0 rewards in every single round for all t for eternity. You're never going to get any reward. All right, but on the other hand, there is a policy pi such that this comparator total reward, right, that is the other term in the regret, is going to be at least, well, it's going to be positive, right? It's going to be at least 1/2 minus p times t, right? So this policy is either the one that always goes left or always goes right? And then just compare these two things, and then you're going to see that regret has to grow at least linearly in this MDP with this sequence of reward functions. So then you can say that, hold on, I mean, we precisely designed this regret definition to protect us against this, right? We wanted to take the effects of our actions into account in the comparator sequence. So like, what went wrong here? So it turns out that the reward function RT in this example was chosen in response to the real state history HT, right? This real trajectory that we went through. And it was not generated in response to the comparator history. So like, our comparator really took parts of this reactivity into account in its definition, but not the effect of HT on RT, right? So I understand that this is maybe a little bit tricky to understand at first. So the bottom line here is that, well, this regret definition is really not suitable for non-oblivious adversaries. So as long as the adversary can play dirty with the past states and pull off things like this, have some kind of reactivity that is not captured by the state dynamics, you're essentially going to be screwed and you have no chance of achieving sublinear regret. So there are two ways out. One would be to consider like real true policy regret in a way that you'd redefine the comparator to take this effect of history into rewards into account. But then basically you should like package this dependence already into the transition dynamics if you want to have sublinear regret or if you want to have a tractable algorithm. So this brings us to this idea that, well, okay, I just assume that all this reactivity is just packaged into the transition dynamics, and then everything else about the adversary is going to be oblivious. All right, so let's just forget about this non-oblivious adversary, this adaptive adversary. This is just way too evil for us, and let's start caring about something that's a little more benign, right? So this is called an oblivious adversary, which is an adversary that cannot take this history into account when selecting the reward in transition functions. All right, so you need to think of this adversary as nature, in the sense that nature does not care about what you do. It doesn't observe you. It doesn't try to like actively mess you up, but it can still be pretty bad. Like I was trying to enjoy a little sunbathing in the afternoon, but then I got the rainstorm. So yeah, that's why my hair is not having a great day. All right, so that's this oblivious adversary, and this is the one that we are trying to act against in the rest of this tutorial. So then the question is, okay, can we guarantee sublinear regret against such an adversary? Can we do anything now in this setup? And turns out that, well, we need to still rule out certain things. So it turns out that learning with changing transition functions, if the adversary is allowed to change the transition functions around in each round, then we're going to end up with a computationally hard problem. So we can achieve sublinear regret in this scenario. There are algorithms, but these are not necessarily always computationally tractable. So formally, this means that there is an adversary MDP problem where the adversary can pick, where the oblivious adversary can pick the transition function and the reward function jointly in a way that achieving sublinear regret on this instance is still going to be computationally hard. All right, so let me just show you this example real quick
Gergely, there
Yes.
is a question from
Yeah.
Vincent. Is the counterexample related to the construction in covers impossibility result?
Yes, it is. It is very much related to that, I would say. I guess like covers impossibility result refers to the fact that no deterministic algorithm can achieve sublinear regret in well, say prediction with expert advice. Well, yeah, or discrete predictions. Yeah. Well, on a second thought, this is not so closely related. Let's talk about this later because this is a bit of a subtle question.
And Amir Masood's asking whether we can put some additional constraints on adversary like computational budget.
Yeah, I'm gonna mention something. I'm gonna mention something in a second.
Okay.
Regarding budget and stuff.
Or slowly changing dynamics or whatnot. I think
that's exactly what I'm going to be mentioning.
Oh.
I have a slide about that, which is coming up.
All
right. But regarding this computational hardness result, here the bottom line is that if you consider this notoriously hard problem of learning noisy parities, it turns out that this problem can be embedded in this adversarial MDP setup. You can construct adversarial MDP instances that correspond to instances in the noisy parity learning problem, which means that sublinear regret in this problem would imply polynomial excess risk guarantees in a computationally efficient way for noisy parity learning, which is conjectured to be a computationally hard problem. Some cryptographic schemes rely on this problem, so it is like really an actual hard computational problem. Yeah, and the construction involves like constructing a specific shortest path problem for each parity example. Really, the bottom line is that this corresponds to an oblivious adversary that picks the transition dynamics and the reward function jointly. So this kind of shows that you cannot really hope to have tractable and nice algorithms for this setup. All right, so this is my side remark that actually, under further assumptions about the transition dynamics, the way that the transition dynamics changes and the reward function changes, if you make assumptions, you can actually have sublinear regret and reasonable performance guarantees. This is very recent work by Pratik Gayane, Ronald Ortner, and Peter Auer, and I guess like a bunch of guys from David Simchilavi's lab. I'm not going to list everybody there. So these works are assuming that the adversary has some limited variation budget in terms of the reward functions and the transition functions. All right. So the first here is the total variation budget on the reward functions, like how much the reward functions drift in total for each state action pair. And the second one is related to how much the transition functions are going to drift during this entire capital T rounds. All right, so it turns out that if these things can be bounded, and in particular, if these things grow at a sublinear rate, then it is possible to guarantee regret. Well, this form, it's like t to the 2/3 times these variation budgets to the power of 1/3. And the algorithms that can achieve this are essentially variations of UCRL that forget all data at an appropriate rate, like with a sliding window or using resets or things like that. Okay, so this is like one way to get around this computational hardness of changing transition functions.
Do these algorithms need to know how fast the changes occur?
I guess, you know, if you want to get this rate, if you want to get this dependence on the variation budget, I think you actually need to know the budgets. If you don't know the budgets, then you get some worse rate that does not get this 1/3 rate, and that is not necessarily sublinear then. I think, but this is really just from the top of my head right now. All right, so this much about like this full-blown problem where everything can change and everything can be adversarial. So in the second half of the talk, I want to focus on algorithms for MDPs with adversarial rewards, right? So we've seen that, well, non-oblivious adversaries are hard. Learning with changing transition functions are hard. Let's just focus on adversarial rewards now and try to understand the main algorithmic ideas there. So this whole line of work started with this paper, or these papers by Eyal Avendar, Sham Kakade, and Yishai Mansour with a Nurip's paper in 2005, which turned into a MARKOV OR paper in 2009. It's called Online Markov Decision Processes. It is really an amazing paper that kickstarted this entire field of research. And what I'm going to do next is just present some of the key ideas from these papers that underlie pretty much all of the work that has been done since in this field. And then I'm going to zoom in and talk about like specific algorithms. All right, so formally we're going to be studying this problem. It's a sequential interaction problem that takes place in a number of rounds. In each round, the learner observes the state xt, and then the learner takes an action at. The adversary selects a reward function that maps state action pairs to rewards that are bounded in 0 and 1. And then the learner is going to earn the reward that corresponds to its state and action. This is going to be denoted as capital R. And then after this, the learner is going to observe some feedback, which is either the entire reward function, lowercase r, or in the case of BANDIT feedback, all that the learner observes is just the reward that it earned, capital RT. And then after this, the environment is going to produce a next state from the fixed transition dynamics, because we agreed that from this point on, the transition dynamics is going to be fixed. All right, so xt plus 1 is going to be drawn from this fixed distribution. And just to make life a little bit easier and algorithm design a little bit easier, I'm going to just adjust this a little bit to say that the learner is actually going to select a stochastic policy pi t in each round, rather than selecting an action, right? So first, the learner is going to select pi t, and then it is going to pick an action at from this stationary stochastic policy. So this is going to be the distribution pi t of the next action given the current state xt. All right, so stochastic policy is, just to recap, it's a distribution over actions given the current state. All right, so this is the protocol. And let's see what is the biggest problem in this learning problem. Well, the biggest problem here is, or the biggest challenge here, is all the crazy temporal dependencies that these key objects have, and all the complicated ways in which things depend on each other, right? So basically what happens here is that the adversary selects a reward function in the previous round. This is going to influence the policy in round t, and the policy and the current state together are going to influence the action that the learner picks. And then this state and action are going to influence the next state. And then this goes on and on and on. And the policy is going to influence the policy in the future, right? So this is a possible schematic for an algorithm that takes the reward function into account when picking the policies, right? So, so this is a reasonable algorithm template for full information learning, because there the reward functions, or well, the actions of the learner do not have direct influence on the policies. I can talk about this more later. So nevertheless, what I'm trying to convey here is that, well, this is a very complicated picture. In order to sort of simplify analysis, what we can do is sort of try to decompose this problem into smaller problems. So let's say that we just start with studying this top part first, the influence on the reward functions and the policies, and try to understand the dynamics in this space, and then worry about the rest a little bit later, about how all this interacts with the actual evolution of the states and the actions. So in particular, the trick that we're gonna pull off is that we're gonna pretend that every policy, or at least in the analysis at first, we're gonna pretend that every policy is going to reach its stationary distribution immediately, right? So in each round t, I can pick a policy pi t, and I can immediately go to its stationary distribution, get the corresponding reward, and then do this in every single round. So just abstract away everything that is related to the exact dynamics. I know that this sounds abstract right now. This is gonna be exactly defined on the next slide.
Okay, so two questions appeared in the meanwhile. Anonymous attendee asks, does this adversary here only observes all the past actions and state pairs that already happened?
Well, so our adversary right now is not allowed to observe the states and the actions at all. So the counterexample that I showed, it works for whatever. If it's only a subset of actions or a subset of states, no, it's hard.
Okay. The other question, Zhang, if we consider the episodic MDP setting and adversary reward and transition, one thing that the agent can do is to reduce the problem into a bandit problem, but each arm corresponds to a deterministic policy. So you have a to the power of s arms, and the problem becomes an adversarial bandit problem, where each episode becomes a time step. Then the agent should be able to get an O e to the s square root t regret. How does this relate to the computational hardness result Gergely talked about?
Yeah, so this algorithm would need to maintain a set of weights for all the policies, right? And this is going to be exponentially large in the state space. So this is not going to be a polynomial time algorithm that is polynomial time in the input size, right? So this is what I mean by computationally hard, that there is no known polynomial time algorithm that that works for it. Right, yeah, but yeah, it's a very good clarifying question. I hope that my answer makes sense.
Yeah. So in a way, this whole thing is about removing the memory barrier or computational barrier.
Yeah, rather computational. Yeah, and both the memories.
Although the regret, it depends on. So should you said that the regret is going to be exponential, but it is actually, if it was the full information setting, right, then the number of actions is going to be in a log. So then you have square root t.
Yeah. So the regret guarantees are going to be reasonable, but the computational time is going to be awful. So it's going to be exponential in the number of states.
And the bandit feedback would make it worse. So.
Yeah, there's probably ways of exploiting the structure and getting something that is polynomial in the number of states. But still, computation will be a mess. Right. Okay. Great questions. Yeah, but so like back to where I was. So what we're going to be doing is that we're going to be pretending that every policy is going to immediately reach its stationary distribution, just to sort of simplify the problem. And here you can see the definition of the stationary distribution of a policy pi, like I guess Ambouge already showed this. So this is really just that you look at the distribution of states over a very long time window, and then you let the time window, the length of this time window go into infinity. This is the stationary distribution. So all of these results that I'm going to be showing are going to be using this assumption about one-step mixing in the MDP that implies that that every policy has a unique stationary distribution, and every policy mixes fast towards this stationary distribution. So here, this number, this tau thing that you see over here, this is what I'm going to be calling the mixing time. And well, we can discuss more on the importance of this particular assumption. Let's just accept that this implies unique stationary distributions and fast mixing. All right, so let's do this. So let's just start working in the space of stationary distributions and see if we can get some ideas for deriving algorithms. Okay, so here are a couple of definitions that are going to be necessary. I'm going to define nu of t of x and a. So this is really just the marginal distribution of states and actions of our policy, of our algorithm, right? So this xt is the real state that we see, and at is the real action that we take. This is the probability that we take state action pair xa in round t. Nu t star is going to be the same thing for the comparator policy, for the optimal policy that you're trying to compete with, right? So nu t star is the probability that in round t, this comparator policy is going to see state action pair x and a. right? And I'm going to define the corresponding stationary distributions as well. So like mu t is going to be the stationary distribution corresponding to policy pi t that I'm playing in round t. And mu star is going to be the stationary distribution that is induced by the comparator policy pi star, right? So now that I have defined all of these, I'm going to rewrite my regret as follows. So my regret is, well, it was defined as this, which I can simply redefine in the form of this inner product or expectation. So what this means is that the regret is really just the difference between two expectations, two expected rewards. One is the expected reward under nu t star, and the other is the expected reward under nu t, right? The actual distribution of state action pairs, right? So this is, I didn't do anything tricky here, but then what I do is that I just add and subtract a bunch of terms to make something more tractable emerge from this expression, all right? So in particular, what I wanted to have is this term in the middle that I'm going to be calling the stationarized regret. So this is really just the cumulative regret in this model where I assume that I can mix immediately. I can go to the stationary distribution of policy pi t immediately in each round, right? So this is really just the total gap between the stationary reward of the comparator policy, the total stationary reward of the comparator policy, and compared in each round with the stationary reward of policy pi t. And the other two terms, I'm gonna be calling these the drift terms, which somehow measure how different these distributions, these nu t star and nu t, are from their stationary counterparts. So basically, the algorithm design is going to be concerned with minimizing the stationarized regret, and controlling the rest, well, is going to be some complicated technical exercise that I'm not going to discuss today. I'm just going to quickly say that for the comparator drift, we can bound it very, very easily, very, very simply by a constant using standard mixing time argument. So this entire thing is just going to be bounded in terms of the mixing time. Again, you can verify these calculations if you feel like it. And the other term, which is this drift for the learner's distribution. So there, the bottom line is that if your policies are changing slowly enough, right? So what this shows is that if the difference between consecutive policies is not too large, then this total drift that you see here on the rightmost term, this is going to be bounded in terms of this change rate epsilon. Yeah, I suppose that there should be like a capital T multiplying this term as well. Yeah, so in any case, what this really means that if the policies change slowly, then this distribution nu t, this actual distribution of the state, is going to track the stationary distribution of the last policy. So intuitively, this makes sense because you're changing your policies very, very slowly. So you're always sort of close to being stationary. And in particular, you're close to the stationary distribution of the last policy that you've played. Again, this is not really part of the central story that I'm trying to tell. So here, what I'm trying to focus on is that, well, just look at this regret decomposition. There are some terms that can be controlled in some really painful technical way, but the real key algorithmic insights come from controlling the stationarized regret, which is really what I'm going to discuss now, like how to actually obtain algorithms from this decomposition, because this decomposition plays a key role in the algorithm design itself. So the two families of algorithms that I'm going to be discussing are what I call algorithms that are based on a local to global regret decomposition, like decompose this whole global regret into local regret minimization games, or well, decompose the regret into local regrets. And I'm going to show you another approach that is based on a reduction to online linear optimization, which is going to use some of the knowledge that that Wouter has introduced yesterday. All right, so first is, okay, so this local to global regret decomposition, as I call it, it is based on this very, very useful technical result that's called the performance difference lemma. So this idea is due to Evan Darkagade and Mansour, but the performance difference lemma has a very, very long history in control and reinforcement learning and in OR. Basically what it says, okay, so if you just look at it right now, it's just going to look like a bunch of symbols and a bunch of letters. It is going to make sense on the next slide, okay? But let me just go through this. It essentially says that, well, let's take two policies, pi and pi prime. Let R be a reward function, and let Q pi and V pi be the value functions that correspond to this R and pi. Then what I have is that the expected stationary rewards, the difference between the expected stationary rewards of pi prime and pi, right? So mu pi prime minus mu pi times R is going to be equal to an expectation of a difference, right? So it's going to be equal to the expectation of Q pi minus V pi, which is, some of you may know as the advantage function of the policy pi. And then the expectation of all of this taken with respect to the state distribution, the stationary distribution induced by pi prime. Okay, so like I said, this just looks like a bunch of random letters, but let's apply it to this particular setup. I just apply this lemma with the reward function being RT, policy pi being pi t, and policy pi prime being pi star, the comparator policy. All right, so then what the performance difference lemma gives us is that the difference between the stationary rewards of these things, I guess this should be RT here. So this is the instantaneous regret. The instantaneous regret is going to be equal to the following thing. It is going to be an expectation over states X of these differences. The difference between pi star and pi t evaluated at qt, right? So this is really like, okay, pi t times qt is the value function. This is v of pi, and this qt, yeah, sorry, I forgot to give the definition. This is the q function of pi t with reward function r of t. So this is what I denote as qt. All right, so this is like already looking somewhat more relevant to what we want. But then we just go from this instantaneous regret expression to the entire regret, right? The cumulative regret. Then we're gonna see that it takes this form, right? We just summed up for all t. But then what we can observe is that, well, since this mu star thingy is independent of t, I can swap around these two sums. And then I can just look at this object, right? So this is the sum over t of the expectation of qt under my policy and the expectation of qt under a comparator policy for every state x. So then the observation in this paper by Evendar, Kakade, and Mansour was that, well, this exactly looks like a regret in a local game in a state x with a reward function qt of x, right? So you can see that if I fix my x here, this is really the exact same form as the expression of a regret in an online learning game where the reward function is qtx blah, right, for every single action. All right, so this is really the best job that I can do at explaining this. What we just did is equate this stationarized regret with a bunch of localized regrets for every state x. So this suggests a very natural algorithm idea. Let's just take a regret minimization algorithm. Just take any of the algorithms that Walter and Alan have been discussing yesterday, and let's just put these algorithms into every single state x and feed these algorithms with qt of x as the reward function. All right, so this suggests this algorithm that's called the MDP-EXPERT algorithm of Evendar, Kakade, and Mansour, which essentially what it does is that after observing the reward function, it just solves the average reward Bellman equations, or the Poisson equations, if you like. It just calculates the Q function, to put simply. Just calculates the Q function, and then it just feeds this Q function into an expert algorithm. To be concrete, I just say that this algorithm is going to be the exponential weights algorithm that we all know and love by now, which really just takes our policy and applies multiplicative updates to this policy, right? So my pi t plus 1 is going to be proportional to pi t times e to the eta times the reward function that I just constructed, the q function that I just constructed. All right, okay, so this is the algorithm that is suggested by the regret decomposition that I've shown. And then the proof of this theorem is just absolutely trivial, right? So this is the performance guarantee of this MDP-EXPERT algorithm. It says that if my algorithms that I'm using in this construction have a regret bound of b of t, then the overall regret algorithm, the stationarized regret of this algorithm is going to be bounded by tau times b of t, right? So sorry, so this b of t is a valid regret bound for this algorithm if the rewards, if the inputs of this algorithm are bounded in 0 and 1. But since we are using it with value functions that are bounded in terms of the mixing time, we have this extra factor of tau in this guarantee. And then if you just go through the rest of the analysis, yeah, if you use exponential weights and if you bound all the other drift terms and all that, then you can arrive to this final regret bound of this algorithm that is square root of t times square root of log number of actions times some polynomial of the mixing time. So interestingly, this bound does not depend at all on the number of states. I'm going to get back to this a little bit later. All right, but again, I don't need to say anything more about the proof because like the construction that I gave was immediately implying the proof here. So there are a bunch of adjustments that you can make to this algorithm. You can adapt it to take care of bandit feedback as well. In bandit feedback, you only observe this the reward that you actually get. Here again, you can just define an unbiased estimator of the reward, as in the EXP3 algorithm that Alan has so kindly explained yesterday. So here, this is really just using an importance weighting trick. But here you have to be careful as to how to define your importance weight. You need to use some special conditions in there. You need to make some other hacks to the algorithm. This is something that we have done with András and Csaba and András back 10 years ago in Europe. Somehow adjust this algorithm to this setup. All right, and then turns out that you can come up with regret guarantees for this variation of this MDP-EXPERT algorithm if you use this importance weighted trick for the reward functions. Right, so in this bound, this beta is a uniform lower bound on the stationary distribution of the stationary visitation probability of every state. In that paper, we couldn't really get rid of this factor. It's not really nice. I'm going to talk a little bit more about this near the end. All right, so then let me talk about this other family of algorithms besides that is not based on this regret decomposition, that is not based on the performance difference lemma, but rather on the reduction to online linear optimization. All right, so getting back to this definition of this stationarized regret, you can actually notice that this is regret in a certain online linear optimization problem, right? You can see that this is like a linear reward that you're trying to maximize with a linear comparator. So this is really just a linear optimization problem. Why don't we just go back to our background in online linear optimization and use an algorithm for this setup? So this is something that Wouter has been describing yesterday in the online learning tutorial. Algorithms that aim to minimize regrets of this form. So in particular, what we want to reduce this to is an online linear optimization problem where the decision set is the set of all stationary distributions. Right, so here we need to regard our decision variables as stationary distributions because our objective is linear in this, and then hope that we can apply this methodology. All right, so here our decision set is going to be the set of all stationary distributions, which is the set of all distributions that also satisfy this stationarity constraint, which turns out to be a linear constraint. So this is a convex set that is specified by a number of linear constraints. So in principle, we can just apply all the standard methodology for it. Yeah, so this stationarity constraint essentially says that if I start from my stationary distribution, I take a step forward in the transition kernel, I'm going to land back at the very same distribution. This is what it expresses. All right, so this is the idea. Let's run online linear optimization on this decision set and with the reward functions as my rewards. So in particular, let's use this online mirror descent algorithm that Walter also described yesterday. We could use other algorithms, but I'm just going to focus on this. So this algorithm is going to perform this maximization step in each round. It is going to try to maximize the instantaneous reward, and it also tries to stay close to the previous stationary distributions, right? So it's going to maximize in the space of stationary distributions, try to maximize rewards while staying close to the previous stationary distribution. All right, and after we have calculated our stationary distribution, we can extract the policy just by marginalizing out the states, right? So our policy is going to be proportional in each state to the stationary distribution that we calculated. So there are a bunch of different ways in which you can choose the regularization function or the Bregman divergence that measures the distances between the stationary distributions. You could use the relative entropy between distributions or the KL divergence, if you like, which leads to a family of algorithms that is now apparently known as online relative entropy policy search, which was first simultaneously done by me and my master student Alex Zimin, and by Csaba and Andris and Travis back in 2014. Right, so that is one possible choice, which I'm going to discuss more, but there are other legitimate choices that lead to very interesting algorithms. For example, using the conditional relative entropy, the conditional relative entropy, where this logarithm is, well, it really involves the policies that underlie mu and nu. Well, anyway, I'm going to be focusing on this choice of relative entropy and online reps. I'm going to describe this algorithm very briefly. What this algorithm does is, again, based on calculating some value functions, but these value functions are somewhat tricky and not very conventional, and then doing an exponential weights update to the stationary distributions. So let me just start with the stationary distribution update. It's going to be a multiplicative update to the previous distribution, where the exponent is the immediate reward plus the expected future value minus the current value. So this is, again, like an advantage function, or like a Bellman error, if you like. So this is what the update looks like. But the value function that we use for this update is the one that minimizes this coast function, or this loss function, which is essentially like a log sum exp of the same thing, of the same advantage function, so to say. So here, what I want to emphasize is that this is an unconstrained convex minimization problem that you have to solve for obtaining your value functions. Again, these are not value functions in the sense of solving the Bellman equations, but rather in the sense of optimizing a certain coast function. And then after you have calculated this, you can calculate your policy update as well. And I have to say that this algorithm is called REPS, or relative entropy policy search, because it's inspired by this algorithm that's called REPS, simply by Jan Peters, Katrine Mueling, and Jasmin Altun from AAAI 2010. So this is a very popular algorithm still in robotics and reinforcement learning, I would say. All right, so again, this is a nice algorithm, and you can prove similar guarantees about it than for the MDP-EXPERT algorithm. So the stationarized regret, which is very straightforward to control, because you just need to use the straightforward methodology of online linear optimization. You just use the same analysis that Walter was showing yesterday to this instance. Turns out that there's nothing really special about this decision set, so everything works out straightforwardly. and you can get this regret guarantee that looks like this: square root of t times log number of states and number of actions. And if you put everything together, take into account the drifts and whatnot, then the regret of this algorithm is going to look like this: square root of t log xa, and there's going to be a factor of square root of tau in this case. So again, the proof is very simple given what you've already seen yesterday. And again, this can be adjusted to work with bandit feedback, or well, at least sort of. So I don't know if anybody managed to adapt this algorithm to work in this ergodic MDP case with bandit feedback. For episodic MDPs or for finite horizon MDPs, we have managed to do this with Alex back in 2013. And in this case, we get a bound that looks like this. The way that it improves over previous guarantees is that it eliminates this assumption of having a lower bound on every visitation probability. I'm going to have a little table that compares all of these. All right, so these are really the two families of algorithms that I think are the most important for this adversarial MDP problem. Well, the question is that, okay, so which one should I use really? So like what are the advantages and disadvantages of these algorithms? So you can, of course, take this very like scholarly approach. You just go to your ivory tower and just compare the bounds and just say that, okay, this algorithm has better bounds, so it has to be better. So if you look at the right column here with this reps algorithm, you're going to see that these bounds are like, well, sort of better. Well, they have some logarithmic dependence on a number of states, but they're scaling with the mixing time, and the horizon in the case of finite horizon problems is better. And another improvement is that for bandit feedback, you actually have no dependence on this smallest visitation probability that you have for all analysis of the MDP-EXPERT algorithm that I know of. So the guarantees of this online reps algorithm are better, but there are some things that this MDP-EXPERT algorithm has going for it. So in my mind, the very important good property of this MDP-EXPERT algorithm is that it works very, very well with function approximation techniques. If you have ways of approximating the Q function, and it's very natural to plug those into MDP-EXPERT. And well, so like this reps approach, I think its advantage is that it's easier to think of if you have like an optimization background, and somehow its formulation allows like plugging in extra constraints or other kind of extensions into its models. So let me just start with this MDP-EXPERT algorithm. Here, if you remember the form of the policies that are output by this algorithm, you can see that, okay, I can just try to like estimate or like approximate the Q functions that this algorithm is using, right? I just plug in a Q hat of t, which is an approximation of the Qt or the Q pi of t that this algorithm was using. I'm just try to calculate an estimate for this, and I can follow this policy, right? Which is like an exponential weights policy that takes all the past Q estimates into account. So turns out that you can derive algorithms with strong performance guarantees for settings with function approximation with this approach. For example, there is this Polytex algorithm by Yassin Abbasi Atkori and others that involve Chava and Peter and Evena and I guess maybe somebody else, maybe Gellert and Kush. Okay, so I think I got everybody. So here the idea is that you just use a least squares policy estimation, policy evaluation, LSPE, to estimate the Q function with linear function approximation, and then you can get sublinear regret, well, up to a linear term that essentially measures how good your function approximation scheme is, right? So this algorithm is and its analysis is really just a straightforward application of this MDP-EXPERT analysis. You just look at your approximation errors in terms of the Q functions and see how they propagate through the analysis. It's fairly simple, and this is really enabled by this algorithm structure. And there's another algorithm that essentially does the same. It's called OPPO by Kai et al. So this is again just using least squares policy evaluation to estimate the Q function, and with realizable function approximation, they can show square root of t regret, which is like the optimal scaling, and they have like reasonable scaling with the dimensionality of the function approximation as well. So this is, well, I guess this really shows that that this is a very powerful approach. You can just plug in your favorite function approximator and still get away with it. And another very strong point for MDP-E is that this algorithm is essentially identical to this very famous reinforcement learning and deep reinforcement learning algorithm that's called trust region policy optimization, or TRPO. So we have a paper with Anders Jonsson and Business Gomez that explains this equivalence between these algorithms. So I guess this really shows that, you know, these ideas are actually very, very relevant to practical algorithm design as well. Yeah, so I was going to say that this OREPS algorithm can include like other constraints and also like involve like other kind of uncertainty modeling in their description. For example, you can just go back to your decision set of stationary distributions and also also extend it a little bit so that P also becomes an optimization variable. The transition model can become an optimization variable that comes from a confidence set of transition models. For example, you can take the confidence set that was defined by Ambouge for UCRL, you can plug this into this decision set and still get a reasonable algorithm. This was first done last year by Rosenberg and Mansour, and it has been extended to BANDIT feedback by Jin and co-authors this year at ICML, where they pretty much managed to get the first algorithm for online MDPs that work with BANDIT information and no prior knowledge of the transition function. But I suppose I don't really have too much time, so let me just conclude here. So, well, there are a bunch of open problems out there, mostly on the front of lower bounds. So I think that still nobody has any idea about what should be the right scaling in terms of the mixing time tau. Like, as you saw, the upper bounds that I was showing, they were all over the map, so it's not really clear like what is the optimal dependence and where should we say that, okay, we know that we can stop now. We don't even know if uniform mixing is necessary for achieving these bounds. Maybe we can guarantee some bounds for communicating MDPs and only assuming bounded diameter. This, I would say, is completely unclear at this stage. There has been some recent progress on addressing large state spaces and function approximation, as I said, but these results are not fully satisfactory yet. So there's still quite a bit of work to be done on that front. But I guess the biggest question is, well, so like, what is really the relevance to practice of all of these algorithms that I've been describing? So I guess the bottom line is that, well, the first set of results regarding negative results, I guess that's just useful for, you know, figuring out like what are the boundaries, how far should we trying to push, where should we stop, and where should we focus our attention a little bit more. And on the front of algorithms, well, you can say that, well, like trying to like figure out these right constants and improving on each other's bounds is like not really what people in practice care about. But I would say that this whole online learning setup is a very, very interesting setup, because it really provides us algorithmic tools that are useful for practical algorithms as well. So in particular, one key tool in all of these online learning analysis is that of robustness. How much does my algorithm change its predictions as my reward function changes? So this kind of robustness is particularly interesting in reinforcement learning. So algorithmic ideas that improve robustness are definitely useful for more practical RL results. And in particular, the tools of regularization that are being developed in this field of online reinforcement learning theory are definitely going to be useful for developing better algorithms. And this is where I always recall that, well, this TRPO algorithm, you know, this is equivalent to MDP-E. So every algorithm that we develop can have similar impact in practical DEPARL as well if you push these ideas and implement these correctly. So I definitely think that this other family of algorithms that I was describing could be one day beating some other algorithms, including TRPO, on interesting problems that some other people care about. So with that, let me just thank all of you and show you this picture from 2010, where a lot of these results that I was mentioning, well, I learned a lot of these results, and we proved it with these two excellent guys that I suppose you can still recognize. So that's András György. I don't know if he's here, but Csaba and myself are both here. All right, so thank you, and well, if you have questions, I'm happy to answer.
Thank you, Gergely. Sharon's asking a question. The analysis for polytext MDP experts was done for adversary MDPs with fast mixing. Isn't there a gap versus what is being done in practice because of stochastic versus adversarial and mixing? If we use an online learning algorithm that achieves good stochastic adverse settings, does it translate to a better RL algorithm as well?
Well, so I suppose if you have guarantees for the adversarial case, then you also have guarantees for the stochastic case, right? So that's true, but of course here you're trying to solve a harder problem. Yeah, and I really don't know. Okay, so I guess I'm just twisting the question right now, but I guess these tools of like robustness and these soft updates and these smooth updates, we know that they are helpful in online learning, right? We know that they lead to sublinear regret, but they may be useful in like dealing with other kind of approximation errors and other kind of errors that arise in large-scale reinforcement learning as well. But like regarding the gap, so like what is the question about the gap? So so as far as I can tell, this polytext algorithm here, you have changing reward functions as well, right? Huh? I'm trying to read that facial expression. So like in polytext, you have adversarial rewards, right?
Oh, are you talking to me?
Yeah, I suppose.
Okay.
So you're the only one I can see. So so in polytext, you have adversarial rewards, right?
Polytech, well, we didn't bother.
Oh, I see, right.
We just focused on the function approximation case, and I just pointing out that it like this exponential weighting applied in a statewise fashion is particularly robust to function approximation errors, which is a nice thing to have. So my answer would be that function approximation is a crazy business. It introduces all types of errors and you need to deal with that. That's almost like an adversary acting on you, especially if you're using neural networks. Have you ever tried that? So maybe it is not too far-fetched to think that these tools are useful. Nevertheless, like turning this into a practical algorithm, dealing with, I don't know, all the practical issues, it takes quite a bit of effort. In the meanwhile, Amir Masood also asked the question. Starts with saying that the composition of regret 3 parts is nice and elegant, but I'm wondering whether we would lose anything in this process. The reason he thinks this is the case is because the drift terms are bounded, using only how fast the MDP mixes, and doing so we disregard the reward generated in the process. Does it matter? Does this matter?
Yeah, that's a great question. Well, I mean, I guess this is like a typical artifact in all these regret analysis, that you really only care about like what happens if T grows large and there's all these big O's and everything. So you just people tend to disregard everything that does not depend on T, but you're right that this may not really be the right approach if you have sort of a short horizon, right? So if your mixing time is very, very large, it's comparable to your total horizon in which you're trying to optimize your rewards, then of course you should never do this. You should do, you should follow some different approach, definitely. But I guess in that case, it's sort of dubious if you can like learn like anything at all efficiently in a way that that nicely exploits the Markovian structure.
I think
Yeah,
the
so,
OPPO analysis uses a different decomposition.
which analysis?
The OPPO. And
no. I mean, they do episodic, so they don't have this decomposition.
So that's helpful. But they overcome the issue that in Polytech we were just sweeping under the rug, which is exploration, right?
No. I mean, they have an episodic setting, so they don't have to worry about
but
it.
even in episodic setting, you have to explore in a certain way to cover things.
Oh yeah, right. So they have exploration bonuses there as well. Yeah. Oh, sorry, I forgot to say.
That's a big difference. But for Amir Masood, just to say that, yes, you can do the analysis in slightly different ways. But of course, in the episodic setting, this all business of drifting and mixing, as it goes away, it mixes. Yeah.
Yeah, right. So there's many papers that care about the finite horizon episodic case. And in that setting, you don't have to decompose the regret at all. I mean, there, all that you have is just this nice part of the regret. These drifts, they just go away.
All right.
There is
I need to run an errand.
There's a question on Discord.
Yeah.
That can the absence of a direct state space dependence in the MDP-EXPERT algorithm, can more be said about that absence?
Oh yeah, okay. So I guess that's another mystery there. So if you just look at these results, right? There you see that well, this REPS algorithm has this dependence on the size of the state space, but its dependence on the time horizon or the mixing time is better. Whereas the MDP-EXPERT algorithm, well, it has a worse dependence on the time horizon and the mixing time, but no dependence on the size of the state space. So this suggests that in some cases one may be better than the other, which is completely mystifying to me, and I don't know where this comes from or whether this is fundamental or not. The only thing that I can like very quickly explain and very briefly is like why these bounds are different, right? Why the stationarized regrets are different for REPS and MDP-E. So for REPS, basically you get a better bound that does not scale with the mixing time because you're directly controlling the distance between the consecutive stationary distributions, and this also improves the drift terms. So that's why you can shave off like this extra tau factors, because you're directly controlling the distance between the consecutive stationary distributions. Whereas if you do this, right, if you just run the MDP-EXPERT algorithm, then you're going to pick up this extra factor of tau here in the regret bound, and you're going to pick up these extra factors of tau also in the drift terms as well. So I can explain like this difference, but unfortunately not the difference in terms of the dependence on the state space. Another mystery.
Thank you. That was very intriguing. Thank you.
Thank you, Ambush, for forwarding the question. All right, so I'm reading a question from the Q&A since Csaba seems to have disappeared. So is it possible to supplement MDP-E or all REPS with an approximate model of the environment dynamics? Which one is more suitable for this goal? For example, if the form of the dynamical equations of the environment is known, but the dynamical map still has non-stationary spectral decomposition. Okay, so regarding the first part of this question, if it's possible to supplement OREPs or MDP with an approximate model of the environment dynamics. I would say that this is easier to do in reps along the lines of this thing that I sort of rushed over, where basically what happens is that if you just take all reps, the original version that considers this decision set, right? Here you know everything, you know what the transition function is, blah, blah, blah. But in a real reinforcement learning problem, you don't necessarily know what P is. And so you can have some sort of uncertainty set of transition functions that you can that you can augment this decision set with. And like what I was describing here is when this confidence set is is of the form of the UCRL confidence set. But of course, you can put like other kinds of prior knowledge about the transition function in here as well. So it doesn't necessarily need to be the UCRL confidence sets that kind of L1 thing is, but you can like input some other prior knowledge of the transition function there, maybe also in the sense that that you were asking for as well. I don't know if that's a good enough question or no. But like whether or not this can be done in MDP-E, okay, I'm not really sure. Yeah, because MDP-E is really apparently better at handling, well, like value functions and value function estimates. So it is more of like a value-based algorithm, if you want to use those terms. Whereas this reps is more like, working in this kind of model space and transition dynamic space. And it's like more convenient to encode prior knowledge into this formulation. If that makes any sense. Awesome. All right. So I suppose it's lunchtime then, or whatever you call it.
Yeah, lunchtime in a certain time zone, the Pacific time zone.
Yeah. Well, here it's almost 9 p.m. Oh my God. My brain can only take so much science at this time.
Yeah, I think we start in about, I don't know, like 20, no, wait a minute, 30, 40 something minutes. Emma will do a tutorial on the batch side of things, batch RL.
Oh yeah, that's awesome. I should catch my breath before that. Yeah, right. So I forgot to say that there's like a bunch of references in there, so I actually took the time to copy them in there.
Yeah, so I think the Zoom just stays on. That's the way it has been, and we just reconvene at 12:30 Pacific, 3:30 Eastern.
Yes, very good.